you will see many standing wave, right? Over there. Huh? You want to see it again? Yeah, I invite you over here. Okay, now we can see no wave. You will see direct sound, right? So what do you see over there? No standing wave, right? That's what I was going to explain to you. So what I explained to them is correct. Okay. So we can confirm the idea, what I explained to you, by just doing the experiment over there, a simple experiment. Or you will hear direct sound, right?
Yeah.
But if you go over there, stand up and go over there. Come from all the directions, right? So certainly what I have been argued is correct idea, right? So radius reverberation certainly also measure the characteristics of room also. Then my question would be, what is the radius of reverberation for free field? What is the radius of reverberation of diffuse field? One of them would be 0. All right? So, and we are happy to give you a last homework tonight, because I forgot to give you the last homework on the last Thursday. So I know this guy is really dislike to have a last homework, but my job is to teach what I have planned. So doesn't matter whether you don't like it or not, but I have to do my, I have to finish my duty, right? Okay, let's summarize what would be the best measure that characterize the room. One candidate is reverberation period, and the other candidate is a radius of reverberation. Okay? Those are related. And I suggest to you to think about what would be the radius of reverberation of diffuse field and what would be the radius of reverberation of free field. And that certainly provides you the concept of radius of reverberation. Okay, now let's move on to another topic. That I call acoustically small space. What does it mean? Mathematically, it means that the size of a space is small compared with the wavelengths. What would be a typical example of those kind? I brought some interesting, very classical, old musical instrument that you like very much after school. Okay. Let's estimate the frequency you can hear from now. What is it? Okay, what would be the frequency? This is 1 kilohertz, right? So obviously this is less than 1 kilohertz. That means wavelengths of 1 kilohertz is 34 centimeter. So obviously wavelengths of the sound that was generated by blowing this bottle would be much larger than 34 centimeter. Therefore we can argue that wavelength is much larger than the typical dimension of this bottle. You agree, right? So I can say that, oh, this is acoustically very small space. Okay? And what happened over here then? What happened over here? Resonance. Why this resonance? Why? Because I excite with excite with the broad frequency, but it generates only 1 or 2 narrow band frequency, that is, which I can estimate the frequency is about 180 hertz, 176 hertz. That is noted over here. So roughly 180 hertz. Okay, because it makes sense, because we drink a lot. Our brain will turn out 180 degree, right? So, you got it? So that's why this is 180 hertz. I think Korean soju maker is very bright, and they tune the frequency to 180 hertz. So that really matches with what happens when you drink a lot, right? So easy to remember, 180 hertz. Okay, now another bathtub experiment. What if I fill more water over here? Pitch is higher than 180 hertz or lower than 180 hertz? Huh? Higher. Higher. Are you sure? Higher? Okay. More water. Higher? Are you sure? Okay. Wow. Great, right? So using soju you can certainly make some music, right? Maybe let's have like 16 students over here, and then I conduct, and we can sing a song using this. Or you can use, for example, wine glass and tune to the different pitch, and you can. And another question is that it will be a very strong candidate of the final examination.